Hi, I'm Josh Cancelier. I'm a product manager at Siemens Miltronics, and I'm going to introduce you to sonic and process intelligence. Let's get started. Here are the topics I'm going to discuss. First, a brief introduction to sonic and process intelligence. Next, I'll discuss how it works. Then, I will talk about some of the advanced features. Then I will show you examples of sonic and process intelligence in real-world applications. Finally, we'll have a quick summary covering the key features of sonic and process intelligence. To understand more about sonic and process intelligence, we need to start at the beginning. In the early days of ultrasonic level measurement, each level instrument required fine-tuning by a certified serviceman to get the best performance. The instruments were large and difficult to configure. Often, return visits were necessary to recalibrate the transmitters. As we solved the easy applications, our customers challenged us to solve the more difficult applications. We spent a lot of time analyzing the information gained in the field to give us a strong understanding of echo processing. This extensive field experience led to multiple echo processing patents. In 1984, we launched our first product with new advanced methods of processing echoes, sonic intelligence. The days of using analog instruments and oscilloscopes to analyze echo profiles were quickly coming to an end. With sonic intelligence, the AirRanger 4 was able to ignore false echoes caused by obstructions and reliably monitor the material level. Since then, we have continued to enhance sonic intelligence, and we have added it to every product in our ultrasonic portfolio. In 1990, we introduced radar technology for level measurement. We adapted sonic intelligence to our radar product line. This became process intelligence. Sonic and process intelligence guarantee repeatability, accuracy, and reliability. The most important aspect of sonic and process intelligence is that it sets Siemens apart from the competition. How? We know how conditions within your process change. We know that the instruments monitoring the process need to keep pace with these changes. Sonic and process intelligence are dynamic. They can automatically adjust to ensure reliable level measurement. In 95% of the applications, our products will work right out of the box. But what if you have a difficult or complex application? Sonic and process intelligence can be easily adjusted to handle any application. How it works. Our ultrasonic and radar products work on the measurement principle called time of flight. Here we see a liquid level application being monitored by an ultrasonic device. The ultrasonic transducer emits high-frequency pulse. This pulse travels down to the liquid level. When the echo strikes the liquid surface, it is reflected back up to the transducer. During this time, the ultrasonic device is listening for the reflected echo. This is shown in the graph window. The graph is called the echo profile. What does an echo profile tell us? The blue line is the echo profile. It is a graphical representation of a digital signal. At the front end, we have a relatively flat area. We call this the noise floor. This is background noise. The large bump on the echo profile is our true material echo. The smaller bumps following the true echo are indirect or false echoes. The line here is called the echo confidence marker. The height of the line indicates how confident sonic and process intelligence feel that this is a true echo. The green trough-shaped line is the echo lock window. The width of the echo lock window represents the measurement tolerance. If on the next pulse the true echo was located outside of the current echo lock window, this measurement would be rejected. Finally, we have this red line. The red line is our dynamic TVT curve. The TVT, or time varying threshold curve, is a mathematically constructed curve to help select the true material echo. Let's look at the sequence that sonic and process intelligence use to select the true material echo. Filtering. If we were to look at a raw echo profile, it would look like this. This is a horrible echo profile. All those small spikes are making it difficult to see the true material echo. In most instances, these spikes are caused by electrical interference. With sonic and process intelligence, the device will automatically identify these spikes by the nature of their height and width. The profile is then processed through a spike filter and we get a nice, clean echo profile. Multi-shot sampling. The typical echo profile is not the result of one pulse. It is the average of a number of pulses. This is called multi-shot sampling. Each device has a different default value for the number of pulses or shots that it takes before processing the final echo profile. The device overlays a number of echo profiles on top of one another. Then, using sonic or process intelligence, it combines these profiles into one average profile. The average profile reduces the noise floor and gives a more accurate indication of the true material echo. TVT, Time Varying Threshold. The dynamic TVT, or Time Varying Threshold curve, is a mathematically constructed curve to help select the true material echo. The position of the TVT above the echo profile is determined by the height of the echoes above the noise floor. In our time-of-flight products, the TVT curve dynamically floats above the echo profile. It allows the device to reliably track the true material echo as conditions in the vessel change. Let's have a look at how the dynamic TVT works. In this example, we see a strong material echo and a low noise floor. As the vessel begins to fill, the echo profile changes, but the noise floor remains constant. We begin to see multiple echoes following the true material echo. The dynamic TVT compensates for these strong multiple echoes by moving further away from the noise floor. Finally, we have an echo that is quite close to the roof of the vessel. We have many multiple echoes. The dynamic TVT adapts to the changes in the vessel. If our TVT curve was not dynamic, we would run the risk of having one of the multiple echoes selected as the true echo. With the dynamic TVT, we de-emphasize the influence of these false echoes and focus the device on the true material echo. The dynamic TVT curve is unique to Siemens ultrasonic and radar devices. None of our competitors have this feature. ALF algorithm. Sometimes you may have complex echo profiles, especially in solids applications. There may be many echoes that are potentially the true material echo. In this case, all of the echoes above the TVT curve will be selected for further evaluation. But which one is the true material echo? One method for selecting the true material echo is the ALF algorithm. ALF stands for area, largest, and first. The ALF algorithm will evaluate all of the echoes above the TVT curve and give them a score based on the amount of area under the curve, the height of the echo above the TVT, and the echo's position along the TVT curve. To give you an idea of how this works, let's look at this example. First, we will look at the area component. Each of the echoes that cross the TVT define a specific area. The echo with the largest area is given the highest score. In our example, this is the second echo. The second component is the large component. The echo with the largest height above the TVT curve will be given the highest score. Again, it is our second echo. The first component is next. The echo that comes first is given the highest score. All of the component scores are totaled, and the echo with the highest total score is determined to be the true material echo. In this example, the highest score belongs to the second echo. This echo would be selected as the true material echo. Auto-false echo suppression. In a perfect world, all of our applications would be on smooth-walled vessels, and the transducer or radar device would be mounted in the optimal position. Well, those applications are rare. In the real world, we have to deal with poor mounting locations. We have obstructions in the tank that can interfere with the material echo. These obstructions can be feed pipes, weld seams, ladders, agitators, cables, support structures, or anything that can impede the transmitted pulse. In this example, the true material echo is the second echo. The first echo is an echo from a pipe entering the vessel near the top. We confirm this by visually inspecting the vessel and comparing the distance to the pipe to the distance shown on the echo profile. If our material echo was always stronger than the obstruction echo, then we would never have to worry about getting a false measurement reading. But what if the material echo got weaker as the material approached the bottom of the vessel? In this case, we have the risk that the ALF algorithm or ALF algorithm would select the obstruction echo as the true echo. How can we eliminate this risk and have the level device ignore the obstruction echo? The answer is auto-false echo suppression. With auto-false echo suppression, we can teach the level measurement device to automatically ignore the obstruction echo. It does this by shaping the TVT curve over the obstruction echo. We can set the autofalse echo suppression parameter with either the handheld programmer or Somatic PDM. I will show you how this is done with Somatic PDM. First, you select the autofalse echo suppression tab. Here we see an example of what the echo looks like before the echo suppression and what it may look like after the echo suppression. The next step is to enter the suppression range. The suppression range is the distance to the true material echo minus 50 centimeters. In our example, the material echo is at 6.5 meters, so we will enter 6 meters into the range field. We then click on the Set Range button and then the Learn button to turn on autofalse echo suppression. The device will now automatically shape over the obstruction echo. When we run our ALF algorithm again, we can see that the material echo gets marked as the true echo and the TVT curve is shaped over the obstruction echo. As the conditions in the vessel change, the dynamic TVT will adapt to these changes, and we can be assured that the unit will continue to track the true material echo. The autofalse echo suppression algorithm can be found in most of our radar products, except for the LR300 and LR400. It is also in our Multi-Ranger 100 and 200, Hydra Ranger 200, and the ProBel-U ultrasonic products. Narrow echo filter. In applications where we have multiple obstructions caused by ladders or weld seams, we can get an echo profile that looks like this. To reduce the likelihood of these obstructions interfering with our true material echo, we can use the narrow echo filter. This filter is set manually. The value to use is based on the width of the echo you want to eliminate. The larger the value, the more of the echo that is eliminated. This is the profile after setting the narrow echo filter. You can see that the top part of all of the echoes have been cut off. It is important to use this filter only on solids applications. The true material echo for solids applications will always be wider than the obstruction echoes. Echo reform. In solids applications, the echoes are typically broader and shorter than echoes in liquids applications. In some of the more difficult applications, we can see some strangely shaped material echoes. I call these echoes two-headed monsters. These monsters are caused by the physical nature of the product being monitored. Most solids do not lie flat in a vessel. When the vessel is filled, the material piles up in a cone shape. The slope of that cone is due to the material's angle of repose. This angle is different for every material. When a transmitted pulse strikes this cone of material, the pulse invariably splits in two. One part of the pulse returns directly to the sensor. The other part of the pulse reflects off the cone and returns to the sensor slightly later. When the sensor interprets these two echoes, it creates this two-headed monster. This monster creates problems when the sensor is trying to select the correct echo. Sometimes it will pick the first echo, sometimes it will select the second echo. If you were to look at these echoes over time, say for example on a filling trend graph, you would see something like this. Your customer would be asking, if we fill the vessel at a constant rate, why do we see such an ugly trend and how do we fix it? Luckily, we have something that will tame the two-headed monster, the echo reform parameter. When we apply the echo reform parameter, we eliminate the two-headed monster and get one echo. Now when we look at the filling trend, it looks like this. Much nicer. I've shown you how sonic and process intelligence work. I have illustrated the use of a few of the basic tools such as autofalse echo suppression and echo reform. In most cases, instruments with sonic and process intelligence work right out of the box. But what about the more difficult applications that don't? In these cases, we can use the advanced features to fine-tune the instrument. Now let's look at a few real applications that illustrate this. Application 1, Dusty Solids. This echo is from a Citroen's LR460 monitoring a very dusty solids application in the food industry. When we first looked at this echo profile, we saw a nice little echo right here. This was exciting because we were told that this would be a really difficult application. Then we did a visual inspection of the silo and manually dipped our level. This is what we saw. That nice echo we saw near the top was caused by a shelf within the silo. Our material echo was somewhere hidden in the mess at the end of the echo profile. If we are to find the true material echo, we are going to have to use some of the process intelligence tools. First, we will use the echo reform tool to clean up the profile and enhance our true material echo. Next, we will use the auto-false echo suppression tool to eliminate the obstruction echo caused by the shelf. Great! Now we can see the material echo. As we monitor the filling, we see that the true echo is continually monitored as the material rises in the silo. The customer was very happy with the performance, and in fact, they have purchased 7 more LR460 radar devices. Tall, narrow silo. Here's an echo profile from another solids application. On this application, we're using a Siemens LU10 ultrasonic transceiver and an EchoMax XPS30 transducer. So what do you think of this echo profile? What could possibly be causing all of these echoes? Well, here's a picture looking down the silo. Each one of these cross members can be seen on the echo profile. The LU10 is set to use the ALF algorithm to select the correct material echo. As you can see, it's doing a fairly good job considering the application. What could we do to help boost the material echo confidence and reduce the chance of falsely selecting one of the cross members as the material echo? The LU10 doesn't have auto-false echo suppression in its toolbox. We could manually manipulate the TVT curve, but with all those obstructions, this would take a while. The easiest thing to do is to use one of the echo filters. The filter we will use is the narrow echo filter. This filter is similar to the spike filter. However, when using this filter, you can select the width of the echo to eliminate. Here's the profile after running the narrow echo filter. You can see how the filter has eliminated the peaks from each of the echoes and given them a flat top. Even the material echo has been affected. However, because the material echo is larger and has more area than the obstruction echoes, the LU10 will have no difficulty tracking the true echo throughout the measurement range. Application 3. Dynamic TVT. This echo profile is from a Siemens LR250 monitoring a bitumen application. Bitumen is a heavy, sticky, black petroleum product that must be heated in order for it to flow. In the vessel, there is a lot of vapor and moisture that eventually coats any surface with bitumen. One of our competitors' radar devices was installed on this application but was not performing to the customer's satisfaction. At least once a week, the competitor's device would set off the high-level alarm even though the bitumen level was far below the high-level setting. This false alarm was due to the bitumen coating the inside of the standpipe. Their radar device would have to be removed from the process and the standpipe would have to be cleaned. Clearly, this is not the ideal situation. Siemens was invited to install the LR250 radar device. This echo profile clearly shows the material buildup in the standpipe, but due to our dynamic TVT curve, the LR250 automatically shapes around this false echo and tracks the true material echo. The competitor's device was not able to do this because their TVT equivalent is static and not dynamic. The customer was very pleased with the performance of the Siemens LR250. Just to quickly recap, sonic and process intelligence are the backbone for reliable non-contacting level measurement readings. Sonic intelligence is used in our ultrasonic devices, and process intelligence is used in our radar devices. 95% of the time, our devices are going to work without any additional tuning because we automatically filter electrical noise, use multi-shot sampling, and have a dynamic TVT curve. In the other 5%, we can use the advanced features like narrow echo filter, the ALF algorithm, auto-false echo suppression, and echo reform to fine-tune the instrument. This concludes our introduction to sonic and process intelligence. If you want more information, we have a number of different documents and resources for your reference. Understanding Ultrasonic Level Measurement by Steve Milligan and Dr. Henry van der Linde. Please refer to Chapter 2, The Sound and the Slurry, for specific details on sonic intelligence. Our product manuals have excellent information pertaining to sonic and process intelligence as well. If you still have questions, feel free to send an email to the e-learning mailbox. Again, my name is Josh Kanzler. I thank you for your time. Take care.